In 1859, telegraph operators across Europe and North America watched their equipment catch fire. Sparks jumped from the wires. Some machines kept sending messages after operators disconnected the batteries entirely, powered by the sky itself. Auroras lit up the night as far south as the Caribbean, bright enough to read a newspaper by. That was the Carrington Event, the most powerful solar storm in recorded history. And back then, the worst it could do was burn out a telegraph network. Today, that same storm would hit a planet running on satellites, GPS, and a power grid with almost no spare capacity. This isn't a threat that can touch your body. It's a threat that can switch off everything your body depends on. Today, we find out what it would actually take to survive that. Welcome back to Space Won't Win. Last episode, we covered how humanity is learning to physically stop an asteroid. This episode is different because you can't deflect a solar storm. You can only prepare for it. If you haven't seen the asteroid episode, go watch it after this one. Subscribe now because this threat is closer than most people realize, and almost nobody is ready for it. Let's get into it. There are actually two different things people lump together as a solar flare, and the difference matters. A solar flare is a burst of light and radiation. It travels at the speed of light, arrives in about 8 minutes, and mainly disrupts radio communication and GPS accuracy. It's fast, but it's usually mild. The real threat is what often follows: a coronal mass ejection, or CME, a massive cloud of magnetized plasma physically flung off the sun's surface, weighing billions of tons. Unlike the flare, the CME is slow. It takes anywhere from 15 hours to several days to cross the 93 million miles to Earth. When it arrives and slams into our planet's magnetic field, it can induce massive electrical currents in anything long enough to act like a wire. Power lines, pipelines, railway tracks. Small geomagnetic storms happen constantly, and mostly they just produce beautiful auroras. But scientists rank storm intensity on a scale. In the top tier, the kind Carrington produced in 1859, is rare. Estimates suggest a storm of that size hits Earth roughly once every century or two. We know it can happen because it already has. In 1989, a much smaller storm knocked out the entire power grid of Quebec in under 2 minutes, leaving 6 million people without electricity in the middle of winter. In July 2012, a Carrington-strength CME erupted from the sun and missed Earth entirely by about 9 days of orbital position. If our planet had been a week earlier in its orbit, NASA scientists estimated the damage could have cost trillions of dollars and taken years to fully repair. Here's where this threat is fundamentally different from an asteroid. With an asteroid, more warning time is almost always available if you look hard enough. Years, sometimes decades. With a solar storm, your warning window is brutally short, and it comes in 2 stages. Stage 1. Solar observatories watch the sun continuously and can usually see a major CME erupt from the surface, giving a rough heads-up of 1 to 3 days before it might arrive. Stage 2. The one that actually matters for precision, comes from spacecraft parked about 1 million miles from Earth at a gravitationally stable point called L1. When the CME physically passes those satellites, we get a direct readout of its strength and speed. That gives us somewhere between 15 minutes and about an hour of precise, confirmed warning before it hits. That data feeds into NOAA's Space Weather Prediction Center, which issues public alerts ranked on a 5-level scale, the same way hurricanes get categorized. Power utilities, airlines, and satellite operators all watch these alerts because 15 minutes isn't enough time to evacuate a city, but it is enough time to do something. It's enough time to reduce load on a power grid, put satellites into a protective safe mode, and reroute polar flights away from radiation exposure. With an asteroid, warning buys you distance. With a solar storm, warning buys you a chance to brace the systems you can't move. The single most vulnerable piece of infrastructure on Earth during a major solar storm is the high-voltage transformer. These are the massive, custom-built units that step electricity up and down across the grid, and the induced currents from a geomagnetic storm can overheat and permanently damage them. That's the real nightmare scenario. Not a blackout that lasts a day, but one that lasts months, because some of these transformers take a year or more to manufacture, and there are only a handful of factories in the world that build them. This is exactly why that 15 to 60-minute warning window matters so much. When utilities get a confirmed storm alert, grid operators can deliberately reduce the load running through vulnerable transformers. Install neutral blocking devices that resist the induced current. And in the most extreme cases, take critical transformers offline entirely until the storm passes. Some grid operators have run drills for exactly this scenario. It won't stop the storm. Nothing can. But it can be the difference between a rough week and a rebuild that takes years. The same warning triggers a cascade elsewhere. Satellite operators put spacecraft into a defensive safe mode, shutting down non-essential systems to protect delicate electronics from the radiation surge. Airlines reroute flights away from polar routes, both to avoid radio blackouts and to reduce radiation exposure for crew and passengers. None of this prevents the storm from arriving. All of it is designed to make sure that when it does, there's still something left standing on the other side. Let's clear something up first, because it matters. A geomagnetic storm cannot burn you, irradiate you, or physically harm you standing on the ground. Earth's atmosphere absorbs the radiation long before it reaches you. This threat doesn't attack people. It attacks systems. Which means solar storm survival isn't about bunkers or protective gear. It's about how well you can function when the systems you rely on every day suddenly don't work. Possibly for weeks. If the grid goes down at scale, the first things to fail are the ones we've stopped thinking about. Card payment systems and ATMs stop working. Physical cash becomes essential. Municipal water systems often rely on electric pumps, so stored water matters more than people expect. Cell towers run on backup batteries that typically last hours, not weeks. So a battery-powered or hand-crank radio tuned to emergency broadcasts becomes your most reliable source of information. None of this requires a bunker. It requires the same basic preparedness that any extended power outage does, just at a much larger scale, and potentially for much longer. You'll see a lot of advice online about wrapping electronics in tinfoil or building a Faraday cage to protect your phone from a solar storm. For the general public, this isn't necessary. A geomagnetic storm's danger comes from induced currents in long conductors like power lines, not from directly frying your phone in a drawer. The advice that actually matters is far less dramatic. Keep some cash on hand. Keep a few days of water stored. Keep an analog way to get information. And know that your GPS and card readers might be unreliable for a while. Preparedness here looks almost identical to preparing for a major hurricane, just triggered by the sun instead of the ocean. For a moderate storm, most modern grids recover within hours to days. This happens somewhere in the world almost every solar cycle, and it rarely makes international news. For a true Carrington-scale event, the honest answer is that recovery time depends entirely on how many high-voltage transformers were damaged beyond repair, because those can't be manufactured quickly. Some worst-case studies estimate regional blackouts in the most severely affected areas could last months, not days, while replacement equipment is built and shipped. This is exactly why grid hardening investment matters more than any individual preparedness kit. The 15 minutes of warning is only useful if the infrastructure was already built to use it. The encouraging part is that, unlike a rogue asteroid, we already know this threat is recurring, predictable in its general behavior, and survivable at a civilizational level, provided the investment gets made before the storm arrives, not after. Here's what makes this threat different from almost everything else in this series. It isn't a question of if, but when. And unlike an asteroid, we don't get to choose whether it happens, only how ready we are for it. The Carrington event proved this storm is possible. The 2012 near miss proved it's still happening, on a timeline measured in decades, not eons. The difference between a rough week and a multi-year recovery isn't luck. It's transformers that were hardened in advance, grid operators who ran the drill, and a public that kept enough cash and water on hand to ride out a disruption instead of panicking through one. Space won't win this one either, but only if we treat the warning we already have as seriously as we'd treat a 15-minute countdown, because that's exactly what it is. So there it is. The sun has already shown us exactly what it's capable of, and for once, this isn't a threat we're guessing about. It's one we can prepare for, harden against, and very likely walk away from, with nothing worse than a very inconvenient week. But not every threat in this universe gives you 15 minutes of warning. In the next episode, we're covering something that gives you none at all. A gamma ray burst, the single most energetic explosion known to physics, arriving at the speed of light with zero warning if it's ever pointed our way. Is there anything you could actually do to survive that? Let me know what you'd want stockpiled first for a solar storm in the comments, and subscribe so you don't miss it. Space won't win.